One, two. Okay, a little bit chaotic this evening because I've forgotten how I do this. Because it's been a little while, but here we are back in the DIY corner. And I'm just pulling myself together. I have my space prepared, and very excitingly this evening we have Moritz waiting in the wings to join us for this thing we're going to be doing, which is exciting. So just give us a moment or two to get myself together, and we will iron out the gremlins as we go, I imagine. Ken, hi, good to see you in the chat. Are you able to just confirm that you can hear and see us, or see me rather? That would be good to know just at this moment. I may be a little bit behind. Audio is good. There's a slight echo. Okay. Try in 1 second. That's muted. I think that's a little bit. There's a little bit of echo. Vision is fine. Okay, look, there's a bit of echo coming from Moritz's mic, but don't worry, we'll work our way through that over time if we can. So, what are we here for this evening? We are here to look at the Synths DIY Compressor. Here's one I made earlier. This is a new module in the educational DIY line of things, and I've done a build video on this already, but this evening the plan, I believe, is to look at it in a little bit more detail onto breadboards. Now, when we did this last year, what I did is that I built it out on a breadboard first in one live stream and then built the module in the live stream after that. Not doing it that way around this time because I've already done the build. I've already put a video out there on that. So this is just to look at the circuit, see if we can understand it better, and to be guided by Moritz himself, which is very exciting. So, as people are coming in and people are still filling out, I will... How am I going to do this? I don't have this. How am I... 1 second. What I will do, I think... It's over there. So what I'm going to do, Mark, is I'm just going to bring you straight in to... and I'll chat to you for a minute and then I'll do that better. It won't make any sense. I'm not making any sense, but that's okay. So, Moritz, there you are, I believe. It's really good to see you, really good to meet you. We haven't had any chance to chat beforehand because I've just, like I say, I've had my hair on fire trying to get this to work. I couldn't find my power supply for my laptop, bits and pieces, you know, stupid stuff going on. But it's great to finally meet you in person. How are you doing?
I'm doing pretty well, thank you. How are you doing besides the stress stuff?
Besides the stress? Well, not too bad as it goes. I've had a week of DIY already. I've been building something which, of course, I can't tell anybody about, as such is the way. But so I'm up for this. I'm ready for this. I'm unpracticed, as it were, but I'm doing okay. So what are you in the middle of at the moment?
I am actually working on my next video, which again will be probably another module. So this time we're trying to kind of time it to be released at the same time, because with the compressor, we kind of did a two-parter. I did my video on the compressor, and then Erica kind of approached me and we're like, hey, do we want to make this into a module? And then I did another video, and this time we're trying to like put it all into one. And so the thing that I'm working on is actually a kick drum, because I've been doing some live streams in which I, looked at the old Roland stuff, so the 606 and the 808, and just like try to figure out like how they work, how they do things. And now kind of like, gathering the stuff that I've learned and then trying to like kind of compile that into like my own design. And the first thing will be kick drum, which I already have on the breadboard. It's already working. There are like a couple kinks I need to work out, but I'm happy with that. The problem is that now I have to write the video, and like coming up with the circuit and making it work is always like much easier than then going in and being like, oh, and now let's look at how everything works, right? Because that like often can be kind of daunting.
Yeah, well, see, the thing that's why we work so well together, even though we didn't know that we did. I'm terrible at all the design and the proper stuff, but I enjoy getting my mitts into things, my mind into things, and trying to understand something. And I'm quite happy to do that naked, if you like, in front of an audience, which is quite good fun. So is this the compressor? Is it the beginning of an intentional new range of stuff, or is it just a one-off?
It's not a one-off. So basically, I feel like the important piece of information is that like I don't do this circuit design and the YouTube channel stuff full time. So for me, it's like still on the side very much. So I have a full-time job, and I only work on these things when I have like spare time, basically. And so last year, when we decided to like release like this entire series, like that was, I did commit to that because Erica approached me and they were like, hey, do we want to do this? And I was like, yeah, sure, let's go. And then I had to feel the pain, because then for a year, I really didn't have any spare time. I was just like constantly, just like designing circuits and writing the manuals and making more videos and just like.
Oh, rats. Oh no, we might have lost him. Might have lost him momentarily, which is a shame. I'll see if he comes back. He'll just come back as a loudly, so we can watch out. We can watch out for that. I knew it was going to work flawlessly. It's quite different. I mean, part of my struggle this evening was to work out how do I have someone actually in this at the same time as me being able to see them or hear them, which I can't. Oh, no, he's back. He's back. I'm
sorry, I got kicked out again.
That's all right. That's all right. What were we saying? Oh yeah, about Yeah, no, I mean, sorry, back to me. Hang on. I'm doing this. I'm being like Nick from Sonic State this evening. This is just, over and above. But, so I'm kind of the same in that I don't do this full time either. So it was quite a commitment for me to do the videos as well on your work. So it's quite interesting how this is sort of panned out. I mean, I think Gertz is very persuasive, and he's the kind of guy that you just feel you want to, whatever it is he wants to do, you kind of want to be on board with it, because he's such a sort of an exciting, and it's an interesting little company to be part of. And I definitely felt that, I would put myself out to be part of whatever it is they wanted to do,
Yeah, exactly. And then, like you said, I ended up agreeing to it, and I ended up like, I think I'm gone again.
Oh, darn it. Oh, we're not having any luck with that, are we? So I'm just going to check at my end to see if there's any sort of problem. One second. It says fair over there, fair as opposed to good, which is not great, but it's better than nothing. I wonder whether it's my end. I've now got your audio, but not video, Moritz. But that might. Oh, there it is.
Yeah, I think it should be back now.
Okay, just let me check at my end. Um, okay. The wonders of technology. Yes, indeed. uh, so, so yeah, tell us more about. So you've got plans for drum modules, is what you're saying, and are those going to be part of this series, or are they going to be something else?
Right. So as I was saying, I hope I don't get cut off again. So basically, the last kind of batch was conceptualized as a batch. So we agreed to release like 9 modules in a batch, and so that's what we did. But afterwards, I kind of felt like I don't want to commit to that again. Like I don't want to
Mm.
commit to like another big batch of modules because that's just like too stressful. I do like to have some free time, and so we kind of settled on this like kind of alternate approach where we said, okay, I'm just going to work on my videos, and if there's something that they're interested in, we're just going to like get together and release it.
Okay.
And so with the compressor, this was like the case. And then with the kick drum, it's a similar. Like I came up with the circuit, I sent it over to them, was like, hey, are you interested? And they were like, yeah, sure, let's do it. And I think this is how we will kind of do it going forward. You know, just when I have something, I'll send it over. We'll make it into a kit.
Okay, great. Well, I mean that works for me in some ways. Let me combine us into a thing. Hang on. Number, is it that one? Let me try that. Oh, look. Yeah, you see, I did do a little bit of work in trying to get this to work earlier. So so the plan for this evening, because these things do take time, as I've come to discover. The plan is that I guess we should jump into the manual and have a look through the circuit. Is that your idea of what we should be doing this evening? Because we haven't really talked about it in any great depth.
Yeah, so I kind of thought like we could like take the manual and then like take the chapters as a guideline, and instead of you having to read it, maybe I could just like broadly like tell you what this chapter is about, and we could look at the diagrams together. Maybe we could look at the simulator, and then you breadboard. How does that
Yeah,
sound?
that sounds good. I mean, I was just having a look through it earlier and thinking that the sort of uh, how a compressor sort of works is something that we could almost skip to the end with, and maybe have a look at this module plugs in at the end of the session, maybe if we've got time, and then we can actually use it in the way that it's supposed to be, as opposed to our semi-working breadboarding efforts. But hey, who knows? Who knows? But so I've got. Hang on, let me just think about myself for a moment. So I did have other ways of looking at this, didn't I? Oh, I didn't quite set everything up as I'd like to have done, but I can bring the manual in. As opposed to having it small the whole time, it's just a matter of got to keep my wits about me on how all of this pulls together. Doesn't matter. So let's have a look. Where are we? So I'm going to come back to the beginning of the manual. Now the manual is on. Let's bring up. Bear with me a second. I can do this. I can bring that up with a thing, with a what's it. So, because it would be good, wouldn't it, to have us all on screen. Put that there. Doopy doopy doo, and that one there. And then I can bring you in there, I think. Oh! This will all become clear in a moment. What on earth it is I'm attempting to do here. There, that's brilliant.
I'm very curious.
Let's do that. So what is that now? That's number 5. So I can bring that in. See, look, seamless.
Oh,
Seamless that was.
very nice.
Ugh. So what we are doing, we are talking about a compressor. So this seems to be something which is quite popular in modular at the moment. I mean, Erica Synths released their own stereo compressor, like, you know, within a couple of weeks of also doing this, and it's something
Yeah.
which is cropped up increasingly in modular, which has been very interesting. So what's the purpose behind this module, Moritz?
So yeah, it's funny. Like I started working on this because someone actually sent me a message, like a DM, and was asking if I knew about any simple compressor circuits. And up until that point, I hadn't even thought about doing anything compressor related because to me, that was always something like, you know, in a DAW. I never, you know, thought about building a hardware thing. And the more I looked into it, like the more interesting it kind of got. And so the basic idea is that I wanted to, with simple components, like cheap components, I wanted to see if I could make something that sounds like good enough, basically. And this, as you can see, I mean, there's quite a bunch of op amps in there, but like generally, like for a compressor, it's quite compact, which is nice. And yeah, if we want to talk about what a compressor does, like I feel like that's to many people that's kind of a mystery. Like even for me, it was kind of a mystery when I started looking into it. Like what does the thing actually do, right? Because it kind of feels like everybody knows that they should put it on their stuff, but then when it comes to like, but what does it do? It's kind of like, well, it makes it sound good, right?
Yeah. Yeah, well, it does. I mean, and you're right. You're absolutely right. It's an odd thing, but also it's, you know, because modular as a sound source is usually so messed up. It doesn't follow any of the rules that you would normally use in a studio in recording. You know, everything is badly done. You're using the worst possible cables. You're using all the wrong sound sources and not mixing it at any point. So things like this, I think, are going to become, or are becoming, more and more vital the longer that we stay outside the door, because all of those tools which are inside your door, the more doorless we become, we're going to need to be pulling these back in from hardware. So it is very interesting. And also this whole sidechain business is fascinating, and I think is another vital part of the musical chain, particularly in the sort of things that we're doing.
True.
And op amps are our favorite thing. We we seem to be using them all the time. So it's one of our favorite things on this show is a good op amp.
Yeah. You know, op amps are so nice because the thing is, like, now that I look at the old Roland stuff, like something that I notice is they often make things extremely complex because they use transistors, and if you use a lot of transistors, you can be more efficient because you can make things, you make less components do more things simultaneously, but that makes it very hard to think about what they're actually doing. With op amps, the cool thing is like you can buffer a voltage, right? And that kind of means that you isolate like one point from the other. So kind of like the input of the op amp is isolated from the output, right? And so for me, like mentally, that's like very convenient because you can be sure like there's no funky business going on between these 2 points, right? It's like these are isolated. So that just makes it easier for me to think about.
Ah, that's really interesting. So I'm still trying to hold these things in my head, the idea of buffer things. I actually do know what you're talking about, and that's a testament to the last year's worth of going through these builds. So so that's great. So is there anything important to point out in this particular circuit, or should we get stuck in?
Maybe one thing. So it does look a little intimidating, but like once we break it down into blocks, it's actually not that bad. There's one thing that's kind of interesting decision-wise. So you can kind of see that the signal flows to the right for the bottom part of the diagram, but then you can see that at the top it flows to the left, right? Because you see all the op amps pointing to the left side, and then it kind of like goes back into the bottom of the circuit. And this is, I think they called it like a feedback-based compressor. So basically, you take the output and you use that to control the operation of the compressor. But that apparently is not necessary. Like when I thought of this, I didn't think of another way, but apparently you could also do it without feedback. You could do it in a way where it's like all flowing in the same direction. But again, I think this will maybe become clearer later. But
Okay.
that's all.
So that we really talked about using this because the side chain works on the compressor, doesn't it? That's the key to it.
Yes.
And it's the sort of thing where you know what the effect is, even if it's quite difficult to describe what is actually happening. But maybe that's what we're going to discover, which is quite exciting.
Yes.
So, so we don't really need to go through the bill of materials necessarily because we're not building the whole thing, but we might have to
Right.
refer back to it. We shall see. Let's skip on through. So the TL074s are our favourite chips. Those, and we've got smaller ones as well. Let's see if I can dig those out. I'll dig a couple of bits out just to have them to hand. Some LEDs, that's exciting. Some sockets. Right, okay, so we're powering up. I better get this sorted first because this, oops, I got those wrong bits because again, I haven't done this for a little while. And I know that my breadboard is upside down and backwards, but that somehow works for me.
Oh yeah, that's actually interesting. Like I watched you like with this dilemma, and at some point I was like, let me check if I made a mistake. And I looked at, this drawing that I did,
Yeah,
and I did use an actual breadboard like to draw it off of. And I checked mine, and actually mine are like this. So this is something that actually it's so strange. Like breadboards it seems to make so much sense that they would be standardized, right? But
yes,
then like different manufacturers, they just do different things, and it's not really clear to me why. Like
no,
there's also this thing where I think your breadboard has like the power lines, they're going like from front to back, right? So the red and blue lines, they're not like cut in the middle. So that means that those rails, they actually connect from one side all the way to the other. But there are breadboards where the red and blue line, where they are cut in the middle. And that is supposed to indicate that the power lines are really cut in the middle. But if you don't know that, and you just assume that they're connected all the way, you're gonna have a bad time because you don't have power on one side of the breadboard. It's bizarre.
yeah. Well, I mean, the way I went forward was simply that that it's the placement of the components which are the most important thing from my point of
Hmm.
view. Let me just come back so people can see what I'm talking about. Yeah. So it's the placement of the components that are most important. So the labeling on my power supply here is back to front compared to what's on the thing. So what I made sure of was to ignore this, I think, ultimately, and just to place it how you've placed it so that I'm doing the same. So I'm doing the same thing, I think. So if I attempt to follow what's in the manual, so at one end I want positive going into the inner rail. That's right. Which says negative on mine, but that's actually +9. Then I've got negative going into the top, which is also being bridged down to here. So
Hmm.
internally, we've got negative, which is correct on the bottom, just not at the top. Like, no, that's not right. Yes, that is right. It goes that way. It goes, no, yes, it goes along. Oh, I'm going to bring your mind together. And then I've got positive down the bottom there. So I've got a rail here, which is -9. I've then got a ground in the middle, +9 at the top. So it actually does sort of work. But anyway, but that should be fine. We're going to assume that that's going to happen and be completely fine. Now let's not break it. So do we want to go through the basics, or do we want to go to um, the building out first? Do we need to go through this? Do you think the understanding compression side of things?
So should I, sorry, I was just gone for a second. Should I quickly like run through this chapter?
Yeah. Okay. Do that. Yeah.
All right. So Basically, like to understand what a compressor does, I found like the best way to get there is to just like look at the waveform before it enters the compressor, and then look at the waveform after it comes out of the compressor. And something that you'll notice is like, so right here on the screen, you can see the uncompressed signal. So that's what goes into the compressor. And if you now scroll down a little bit, you can see here, this is the compressed version. And at first glance, you might think, oh, it's just like quieter, right? We just turned down the volume because you can see that the waveform is like the height changed. But if you look closely, you can see that the small parts of the waveform, the little blips, like they're actually the same as they were in the uncompressed signal when it went into the compressor. The only thing that really happened is that like the loud parts, like the really big things up top, like they are like really squashed at the bottom. And so that's actually what a compressor does. Like it kind of looks at the signal and it says, okay, this bump is not too loud, so I'm not going to touch it. This other bump is way too loud, so I'm just going to turn down the volume. So yeah, it just constantly looks at the signal, and whenever the signal gets too loud, turns down the volume. That's like roughly what it does.
Nice.
Right, and then there's like a bunch of additional controls. Like if you're in a DAW and you look at like the plugin and what it gives you, there is usually a threshold. There's usually a ratio. There's usually an attack and release, and then there's a bunch of other things like the knee and makeup gain and whatever, which we don't care about at the moment. So what I just described basically is mostly about the threshold. So the threshold is what tells the compressor like which sound it should consider as too loud. You can see it like in the drawing, like if you look at the input and output, you can see this little like dashed line, and that would be the threshold. So anything that goes above this threshold would kind of trigger the compressor, would tell the compressor like, oh, this is too loud, I'm gonna have to do something. And then the question is kind of like, okay, but how is the compressor going to reduce the volume? Because it could do that in a number of ways. And those ways, like it depends on what the attack setting is, what the release setting is, what the ratio setting is. And basically, in this first diagram, like what I demonstrate is we have the attack and the release turned all the way down. So we can kind of ignore them for now. And what's important here is the ratio. So the ratio, you can see that it's dialed up, but it's not all the way at the top. And that means that the compressor won't cut off the signal at the threshold, but instead it will let the signal come a little bit above the threshold before it kind of cuts it off. You can see that there because it doesn't stop at the dashed line, but instead it goes slightly above it.
Okay.
And so if you would change the ratio setting, if you would turn it down, then the compressor would allow the signal to go further beyond the threshold. Or if you would turn it up, if you scroll down, if you turn it all the way up, which you can see here, the ratio is like at infinity to 1, then you can see that the signal is actually cut off at the threshold in the output. Does that make sense?
Yeah, no, it does make sense. Yeah. Yeah. I mean, ratio I've always seen as being, I don't know what I've seen it as, because compression is one of those things which you just kind of use rather than understand.
Yes.
in my experience.
Exactly.
So no, that's very interesting. Yeah.
Right. And then the other two controls are also kind of interesting, attack and release. And like I said before, like in this scenario right here, we have them both dialed completely down. So what that means is that if there's kind of zero attack time, that means that the compressor activates instantly. So the moment that the signal crosses the threshold, the compressor reduces the volume. And then the release is kind of the symmetrical counterpart to that. So if the release is 0, this means that the compressor stops compressing the moment that the signal falls back below the threshold. And what that does to the signal is that it's like really violent because it just chops off the peak. You can see that like in what I've drawn, like I've tried to make that obvious, but it's almost just rectangular at the top. It's just like sawed off. And if you do that, then the compressor actually acts as a limiter, which means that it does not allow under any circumstances the signal to get louder than the threshold. And you get like a very almost like distorted sounding output from that. Like it's very like rough.
Yeah.
Yes. And then, if you don't want that, which is probably often, then you would play like with these three settings, with the ratio, with the attack, and with the release. Because if you dial down the attack, I think if you scroll down a little bit, Robin. Right. So what I show here is that you can see that the attack dial has come a little bit up. And in the drawing, you can, it's not really easy to see, but you can kind of see like the bump on the left now has like this initial transient, we call it, which is just like the initial snap of it, like that comes through. So the compressor allows that to like come through, and then it reduces the volume. So that way you can kind of like emphasize like this snap at the beginning of the sound, basically.
Yeah, gotcha.
And then with the release, like if you scroll down further again, right, so here with the release, what I did here is like I turned down the attack again, I turned the ratio all the way up, and then I turned the release up a little bit. And what that does is that the compressor now reduces the volume even after the signal has already dropped back below the threshold. So that way you can see it's not sawing off the top anymore, but it's like it's reducing the whole sound. Like it's making everything more quiet, basically.
Yeah. So the change is less severe, I suppose. You've kind of got
it just sounds more. It sounds more natural, definitely. Yeah.
Excellent. Ooh.
Right. And then in this part, basically what I do is like, this is actually how I came up with the concept of the circuit. I thought about, okay, now that I roughly know like what it should do, question was like, how do I make that happen? And I tried to this time just approach it from like from a position of just like very high level, like on a high level conceptually, how could we do it? And I kind of thought of, well, first of all, we need something that can take in an audio signal, that spits out an audio signal, but that we can control the gain factor of. So you can see that here, I call this block the volume modulator. You can see it has an input on the left, it has an output on the right, and then it has a CV control up top. And, basically the idea was like, okay, so somehow we want to take the output signal. We then want to look at how loud it is. That's what the volume detector block is. And then we want to compare whatever we measure to a threshold, like that would be the threshold dial that we saw up top. And then we want to make a decision. Is the signal currently louder than the threshold, or is it currently quieter than the threshold? And for that, we would use this block, which I call a volume comparator. So it just compares two volume levels, basically. And then whatever that thing decides, I would want to use to control the first block. So we get kind of a feedback loop that goes like this. So the volume modulator gets an input signal. It spits out the input at the output. We measure the volume of that. We decide if it's louder than the threshold. And if it's louder than the threshold, then we're going to turn down the volume modulator, like the volume of the volume modulator.
Yeah.
And that's all like on the very basic level.
Yeah. See, I know there's a circuit in my head, you see. I'm starting to see bits on a transistor where you have something which compares to something. I'm sure that's going to rear its ugly head in a moment.
Probably, yeah.
Yeah.
So, right, and then now what we kind of want to do is, so we have these four blocks like conceptually in our heads, and now we want to like go ahead and find like actual implementations for that. And the first thing that I tackle here is basically this volume modulator block. And maybe like when I talked about, maybe you already thought about a VCA. Like for me, that was like the first thing that sprung into my head, right? Like if you have a modular, and I'm gone.
Oh, rats.
All right, sorry, I was gone for a second.
That's all right.
Okay. So yeah, as I was saying, so you know, if you're into modular, like, and you hear about, okay, I want to modulate the volume of something, you instantly think of a VCA, right? Like that's just how you do it.
Yes.
And so that was my first thought, and I then first thought about reusing the VCA, you know, that we released as a kit, also that you also built, Robin. But I kind of like didn't want to repeat myself. It's probably a vain thing, but I wanted to try something out.
No, fair enough.
And so let's make a different VCA. And I had this idea like floating around for a while, and I think I liked it because it's actually, I think it's easier to wrap your head around than the other one. You know, if you look at the diagram, you see like a bunch of op amps, but the circuit itself is really just the diodes in the middle that you can see. The 6 diodes.
Yes.
And then I'm gone again.
Gosh darn it. Is it? Oh.
Sorry, I was gone again. Sorry, what were you saying?
I don't think it was important. You were talking about the diodes.
All right, so right, I was just saying that like in this diagram, the important part is just like the 6 diodes and the 100K resistor. Like you see how the 100K resistor like kind of connects to the middle of the diode string, right?
Yes.
So that's like the part that we care about. Everything else is kind of like, we'll get to it, but it's not essential. So if you scroll down.
Yep, sorry. Yep, hang on.
Right, so yeah, right here in this diagram, like I stripped away like all of the op amps, all of the other stuff, and I just stripped it down to the diode string, and then the resistor. And you can see here a scenario where basically on the left side we have an oscillation, and then at the top we apply 0 volts, so ground. At the bottom we apply 0 volts, so ground. Now the thing with voltages is like you only get a current if there's like a difference in voltage, right? If you apply ground at the top, ground at the bottom, then nothing will flow through the diodes, right? They will just be kind of idle. They won't be doing anything. And now what basically happens is you have the oscillation on the left, and you have like, that's supposed to be like a measuring device on the right. And what you're going to measure is the same oscillation that you put in. And the reason for that is that in this whole system, no current can actually flow, because we do push from the left side against the resistor. But there's no way for the current to actually go, because the diodes are essentially off. Like they're not conducting. They're just like sitting there idle. Nothing is happening. And the thing about voltages is, like, the curious thing is like they stay the same if no current flows. And so in our scenario here, no current flows, so the voltage on the left is going to be the same as the voltage on the right. So we just reproduce the same oscillation that we put in. And so this means that our VCA is basically not reducing the gain. So we get input equals output, basically.
Okay. So
does that make sense?
Yeah, so the resistor in this instance isn't actually doing anything.
Exactly. Yeah.
Okay.
Like in this scenario, it's not, it could just, might as well just not be there.
Interesting.
Right. And then, right, if you scroll down, like we can see here, this would be like the opposite scenario. So now we apply 2 volts to the top of the diode string and minus 2 volts to the bottom of the diode string. And that's going to make sense in a second, because you might ask, like, why not apply like 2 volts and 0 volts, right? But like essentially, like what this does is, like, we have a voltage difference between top and bottom, and that voltage difference is actually quite substantial, so 4 volts. And this will cause a pretty big current actually to flow like through the diode string. And now comes the part with the 2 volts and minus 2 volts. The trick here is that these diodes, like taken together, they form something like a voltage divider. And the interesting thing is that, or the important thing is that, like, the diodes all have roughly the same resistance, if you will. It's not really resistance, but it kind of acts like resistance in this scenario.
Okay.
And if you, like in your head, if you replace the top 3 diodes and the bottom 3 diodes with one resistor each, and you would say, I don't know, it doesn't really matter, but let's say the top resistor is 100K and the bottom resistor is 100K. Then you have a 50% voltage divider, and a 50% voltage divider like slashes the voltage in half. And since we have 2 volts at the top and minus 2 volts at the bottom, this means that the node in the center will be exactly halfway between 2 and minus 2, and that's 0.
Okay.
So then we have basically ground level in the middle. And this is important because now what happens is that we have the oscillation on the left, right? It's like pushing and pulling on the resistor. And we chose the resistor to be pretty big, actually. And we did that because now we push and pull like a little bit of current kind of from the diode. So we pull current from the top 3 diodes, and we push current through the bottom 3 diodes. But the amount of current that we kind of push and pull into and from there is like really negligible in comparison to like the amount of current that flows from top to bottom. And so the voltage in the center is like barely affected. Like if you really wanted to affect it, you would have to push a large amount of current into it or pull a large amount of current from it. But since we don't do that, since the resistor is so big, the voltage in the center basically stays unaffected. So it just like sticks at 0 volts and that's it. And so we like kind of just killed the signal. So on the right, nothing comes out anymore. We put something on the left, but on the right, it's just gone basically.
Okay.
And also, like, I don't write this here, but the like there's all the in-between states, right? So the 2 volts minus 2 volts is kind of like a big difference. But if we reduce that difference, if we go down to like 1 volt and minus 1 volt, or 500 millivolts and minus 500 millivolts, like the current going through the diode string gets less and less. And so the ability of this kind of stream to wash away the signal diminishes. And so actually we get a louder signal at the output. So the more we reduce the voltage difference between top and bottom, the louder the output signal will get.
Okay. Yeah.
And then, you know, for the part with the op amps, like they just facilitate that basically. So they just like take our signal and they take our CV and they make sure that we have this current going through the diode string. And they also apply the signal to the diode string. And there's like one small missing piece of the puzzle, which is that we take the input and we scale it down. So you can see that you have the signal there on the left, and then you have a voltage divider right next to it.
Yeah.
And that voltage divider is actually quite aggressive. So it's like 100K and 10K. And that would divide it down by a factor of, I think it's 11. So if you take a 5 volts peak-to-peak signal, which is like 10 volts peak-to-peak signal, which is like in Eurorack the standard, you would get something like 500 millivolts, something like that. And we need to do that because like this is where the design kind of has its limitations. The thing is like if the input we apply to the diode string is like too loud, then or like too strong, then that input can actually make the diodes conduct by itself. And this would give you distortion. So that would kind of cause the signal to like kind of sound very hot and like kind of just like mangled in a way. And so we have to like really make it quiet so that it doesn't do that.
Okay. I gotcha. Right. Okay. Yeah. So we're gonna we're going to test this out on our little board here.
Sure.
Is that the plan? Should we do that? And let me just bring my board in. So everyone following along at home, we're going to try to work out. So down this bottom left hand corner is a whole bunch of diodes all looking and facing each other alarmingly.
Right.
So we're going to need to start off with our, I need the glasses on for this. How am I going to get, oh my goodness. That's not going to work. So I've got headphones on. Wait a second. I don't know. Anyway, we'll see how we go. There's only the one chip, so it's got to be that one, right? So I've got a magnifying glass. It's just that my eyes aren't good enough to see what on earth anything is very much. There you go, 74. That's the fella.
Yep.
So this is the chip that we need. I'm just going to give it a squeeze. So this is a bunch of op amps. It goes this way round. It looks like one leg goes on 20. That leg there. That seems about right. Right, so we've got a bit of faffling to do. We're going to have from the outside come into number 7. 567. Like that. We've got, where's my box of, I've got a yellow one here that might fit it.
Robin, I'm actually very happy that you now have these kinds of jumpers, because I remember like last year when I was watching in the beginning with the wires.
Oh yeah,
kind of painful.
It was painful, but you know, I was making do. I think is the. I'm a big advocate for just getting on with it rather than being delayed or anything because you don't have the right gear. You know, if you can make it work, just get on with it. So but no, this has helped greatly. I'm just going to get a few of these out so I can make use of them.
I mean, actually, there's something to be said like for these cables, because they give you a little bit more freedom, right? Like you don't have to have the exact match, so you can just like wing it. But once you get to a complex layout, it's just gonna, kill you.
Yeah, it is. Yeah, it did get a bit crazy in there. So that's 15. It goes up to 14, I think. So I think that goes there. So if people are watching, you've not seen this before, it does take a bit of time. That is just the way of things. Now there's a tiny one here which connects these up. So on the breadboard itself, what happens is that you have connections going this way, going across the board. So we're trying to make like this wire here is coming in. It's connected to this. It's also connected to this pin on the op amp. So this is how the circuit is built out. So it won't look like the circuit diagram particularly, but you start being able to identify stuff. And the layout on here just has to work, so it's not necessarily representedly visually like their circuit diagram is. But it does all start to come together. What's going to be more difficult is identifying my resistors in a minute, but we'll get to that in a second. So I'm going to need patch sockets. Those are over here. Those bits out. Let's find my resistors. So for this, there's a couple of 10s, a couple of 100s, a 2K, a 330K. Had I thought about this, obviously I would have measured these beforehand, but hey, I did not. So, but I've learnt now that anything that's got a 1 in it is going to be reds and blacks and browns and things like that. So let me get my nice little multimeter.
It's actually kind of the bane of my existence. So, my desk is constantly just like full of like resistors that I was too lazy to bag correctly in the moment.
Yes.
And so I always have like these moments like at the end of the week when I'm like, oh no, I have to sit down now for like half an hour with a multimeter and just, test all these and then stash them away. It's horrible.
Yeah, I absolutely know that. So that's a 220K. That's of no use to us at this point. Put that away. So let me find. There's going to be more of these. See, that's a 33. Did we need a 30? We need a 330, and that's a 33k.
That's not quite what we need, yeah.
See, I'm sure there's a machine that I can just stab these into rather than using these bloody crocodile clips. But that's 100k. Okay, so that's me 100ks. I'm going to need a bunch of those. So that's those
Very
ones.
nice.
I'm even going to label it because that's helpful. 100k. And that's 10k.
So how many breadboards do you have, Robin?
I have, it came as a pack of 2.
All right. I feel like do you feel like yours is so I feel like the cheaper ones, like they lose their grip on the holes. So if you use them a bunch, like they just kind of like don't make contact anymore. Do you feel like yours is doing that?
I don't think I use it anywhere near enough for that to happen. But
Right.
and also, you know, once you've started building out the circuit, particularly in this sort of environment where I'm trying to be on camera, so I'm not comfortable. You know, I've got a microphone, I've got stuff around, I've got headphones on for heaven's sake. You know, and so the fact that anything works at all is quite a miracle. So you know, I've got the patch sockets are never staying in. That's 470. Am I going to need one of those? I don't think so. Did I do that one? Oh, see, I'm getting myself confused now. I need to focus. That's 10. That's 100. I know those ones. That's a 10.
Oh yeah, Ken just suggested in the chat that you should get a component tester.
Yeah.
Actually, I've also been looking at these. I think like I did a workshop once and someone like brought one of these and it was like ultra handy. It's so nice that you can just like plug it in and you just know instantly and you don't have to bother with the crocodile things.
Yeah, absolutely. So that's for 330. So I'm going to stick this one in while I've got it in my fingers. So this is over on line 30 here. 31. It's going from there into there.
So Robin, modular bias asked like kind of like a question, like a provocative question. He asked if you shouldn't be able to tell by the colored lines now.
Yes, except my eyes just aren't good enough, and I can't put my visor on at the moment. I've just unfortunately fired a resistor somewhere. I wonder where that went. Let's assume it's not one that we want. Otherwise, I'm going to have to dig around. But yes, I would like to be able to identify just by looking at them, but that just doesn't seem to work for me. I find the whole color banding thing is so inconsistent in what actual color it is that again, it's one of those things that they should have had a system. You know, there should have been something. So that's 470k. I don't think we need that one just at the moment. Nearly. What was I'm after? Just after a 2k. That's all I'm after now. It's going to be the one that fell on the floor, isn't it? I know it. I know it. 120k. Oh, that's one of those funny weirdo ones. I had no idea what that was the first time we saw it. It's like a was it a block or a something or other?
Oh, is it like one of those 0 ohm resistors?
There we go. Yeah, 0 ohm. So that's 20k. That's nearly there.
Yeah, I'm not entirely sure. Like, I think that the point of those is like if the person that made the PCB like just couldn't figure out a way to make a bridge somewhere, and then they give you these to like just make a bridge essentially.
I gotcha. So this is the 2k one. I'm going to stick this one in as well so I don't forget it. So let's bring this back into shot. So the 2k, Ooh, that's tricky to see. It's going from 0.20 up this end on this second one, and it's going down to what I think is 13.
Oh,
Could be
NTO
14.
Steve. NTO Steve just said they're all the same. I think he is referring to the color banding, and I think he's right, but I think you meant like the color of the body, right?
Well, the color of the body, but also um, whether is it brown, is it orange? You know, that's I think highly selectable.
Yes, that's true.
And also, is it the tolerance or is it the number? I get that very confused, and how two resistors can have the same resistance even though they seem to have different band of colors on them. I know they're supposed to be the same, but that just, in my limited experience, I find that very confusing. So I like to
Right,
be able to ultimately measure them, or do it because it says that there's 5 of these and I've got 5 of them, so I'm just going to assume that that's right.
yeah.
So this patch socket here goes from this line, is the 0, because this outside one, no, I don't know, hang on,
I think that's ground, yeah,
yeah, yes,
for
yes
you.
it is, yes, that's right. So that's right. Think about it. So that's going to go about there. So we want 100k, which is one of these ones here. So this is going to go from there to there. So this needs to go. I haven't quite got the room. Why don't I have the room? Ah, I see, because you've nipped that down just one more,
Right.
just over the gap. This takes the signal from the back of the patch cable and goes into pin, or the third pin down. I'm not going to say it's pin 3. I forget how the pin outs work. It goes like that. That's 100k. That's completely wrong. 1 second. 1, 2, 3 up from that end. 1, 2, 3.
Right.
Then that goes in there. I've got a
Okay, so
10k.
John just asked if there will be a new case as the compressor won't fit in the original one. It's a good question. So basically, I haven't talked to Erica about it. I think so far, like the assumption was just that you could just get the other case again. Um, Now that like probably it's gonna go more in like a percussion direction. Like I kind of feel like it wasn't intended like that, but the compressor kind of like fits well with like more percussion stuff, so kick drums, hi-hats, snare drums, and so on. So yeah, I think I might talk to Erica and maybe suggest that we do like a percussion themed case, however that would look like. I'm not sure. Maybe you have some suggestions in the chat.
I think that's a great idea. That's definitely a good complement to the essentially you've got a synth voice, haven't you, in the original one? That would make a lot of sense.
Right. Oh, by the way, Robin, like when it comes to effects, like for your modular, like what's your preference? Like delay, reverb, what do you like?
I like a good delay. Um, well, delay and reverb, really. I mean, you in multi effects, that's all I ever use. I think whenever I've got a multi effects unit, it's always delay and reverb that I use. Occasionally chorus. Most things already have their own overdrives, so, and I do have a couple of extra ones of those, but I rarely use them because most often filters have a form of drive in them, or in other places. So I'm not needing distortion anywhere particularly because that seems to find its way in regardless. But delay is usually the most interesting. Reverb obviously gives you a good spread of stuff to enjoy. But delay is probably the most creative. That's always the thing I'm going for, I think.
Mm.
most instantly satisfying.
Right. And then like when it comes to types of delays, like do you prefer analog ones or digital ones?
Um, I don't really mind, just as long as it gives me enough little bit of time to be ambient. Sometimes with analog delays are a little bit too quick. I'm not particularly
Mm.
into the sort of comb filter phasing type thing. I prefer it to be an echo, so I hear it later, but also not necessarily a tape echo, because they drive me nuts as well. I've I've spent a lot of time fighting with the magneto, trying to get something that I understand out of it. And often it's like I don't know what's going on, and then a couple of minutes later, oh look, there's my signals just coming back through. It's a weird thing. So I just quite like a straightforward. Having been a guitarist, in well, I still am a guitarist, but I like a digital delay where I feel like I'm the edge and I can rattle off um, delayed guitar lines that make some kind of sense in a musical context.
Right,
That
that
goes
makes
there.
sense.
Right, so I've got all my diodes about to go in over there. I think I'm going to do everything else first, do the diodes last. So we're just starting to come down here.
Yeah, the diodes are a little bit messy, I have to say.
So this goes from 5 to... Does it go to that leg of that 2? No, not quite, just before it. Has that gone in? That's the question. I don't know. Let's try another one. Sometimes they just do not behave. See, that went in perfectly. What was all going on about before then? What was all that?
Like
Okay,
sometimes breadboards can be really unpredictable, I have to say.
right. So I need another 100k. Goes into up to 15. Is that on the same leg as the 2? Yes, it is. Up to 15.
Oh yeah, you want to have hear a fun breadboard story about this circuit?
Yeah.
So basically, like when I had the design finished and I sent it over to Erica, they made a prototype and they sent me the prototype, and I got very excited and I, just set up my soldering iron and started like putting it together. And I was very sure that the circuit will work. And I assembled the module and I put it into my rack and I turned it on, and it just produced like the most horrible noise, like really weird brownish noise type of thing. Like you could barely hear the input signal. And I was completely like dumbfounded as to what went wrong. And I just lost you again.
I'm sure he'll be back momentarily. It's not as if I don't have anything to be getting on with.
I'm sorry, I
That's all
just
right.
lost you.
I don't know what it is. It's just one of those things.
Yeah, I guess so. So yeah, basically, I assembled the module. It sounded horrible. I didn't know why, because I was sure that the circuit would work, because I tried it on the breadboard. And I tried a bunch of things, but nothing seemed really fruitful because I kind of thought, well, the circuit is correct. It should be correct because it's working in this one context. And what was blocking me was just like this thought that, like, normally a circuit gets better when you move it from the breadboard to the PCB,
Right.
because breadboards are kind of crappy. Like they have like all kinds of like little errors and problems that make them sound worse. And the PCB will usually be more clean. So my expectation was once the circuit jumps to the PCB, it should sound better, not worse. And at some point, like I talked to people on my Discord server and I explained the problem to them, and someone pointed out like, hey, did you think about the fact that maybe the way that the breadboard is crappy actually in this case makes it work, you know? And I was like, man, that's an interesting idea. And I thought about it and I kind of realized, so the whole circuit is a feedback loop. So we feed the output back into the input, and that's like very prone to like start oscillating because, you know, the slightest bit of noise that enters the system will kind of just like go into an infinite feedback loop, and then we'll just like, get very loud. And I kind of started thinking about, okay, so how could the breadboard prevent that? And the thing is that inside the breadboard there's like these long metal claws that are like one kind of like long thing underneath every like row basically, and those things basically act as capacitors. So they have like a very like small amount of capacitance, so that they will store a charge kind of.
Okay.
And we call that parasitic capacitance the breadboard has. And it kind of occurred to me that maybe like that is what keeps like certain op amps in the circuit from starting to oscillate.
It's very weird, this disappearing. I don't
I'm
know.
back.
It's
I'm back
funny.
again. Yes. So yeah, this parasitic capacitance of the breadboard, basically what it did was like it kind of cushioned out like the
Oh, darn it.
All right, I'm back. Let me try this again. So basically the capacitance of the breadboard kind of cushioned the op amps and made them like not oscillate. And
Right.
I verified that by just basically taking like a very small capacitor and like just soldering it to like 2 points on the PCB, and it fixed it. So that just like fixed it right away, just one small capacitor.
How weird.
And it was super weird, but it was also just like very like satisfying because the problem was so absurd, right? It was so strange, and I didn't know what the fuck to do. And then I did that, and all of a sudden, works.
Nice. Right, well, I'm nearly to the diode bit.
Right.
This is assuming that anything else is in the right place, but we're going to go. We're going to go with it. Okay, that needs to be there. And then you need to push those out either side.
Okay, so in the chat, John asks, how do you spot a good quality breadboard? It's actually an interesting question because they all look very similar, right? Like if you go into a store and you look at what they have, they're all going to look roughly like this. And it's very hard to like just judge it from what you're seeing. And so I think the best method, unfortunately, is just going by price.
Yeah.
You can usually, like if you just go for a more expensive one, often they will be better quality. But there's actually, there is a video by this guy called Ben Eater. I don't know if you know him. He does like really crazy breadboard stuff. He builds like an 8-bit computer on breadboards.
Right.
It's really crazy. And he has a dedicated video just talking about how to spot a good breadboard. So I highly recommend watching that.
One, two, three. Good. That's there. That's there. That's there. That's there. That's there. That's be 30k. That's going off the tip of that. That's connecting to that. There's a line. That one. A little one. That one. 100k there. Cross the line. Over there. It's crossed. It's done that line. There's the 100k, 2k, 100k. Little one. Bop, bop, bop. Right. Diode time. So I'm going to have that the right way round. Going from the 100k. It's going to 1, 2, not next to 1. That's going that way around, goes from the edge of that one, so they're all connected. And that goes to, looks like it's 11. 10, 11 to go next to that one? No, it goes one in from that one. Okay. Next one, same line, goes from the end of that one to the line in between, next to the 100. Line in between. Okay, so that's 3 of them going to the 100k. Coming out the other side, I've got, that's a resistor, so that's not going to work. Let's try a diode. I've got that going that way around, coming from the front end of that to 1 past it, so front end to 1 past it, that way around. That must be the end of it. And then this goes to, not sure, where does that go? Not the 100k. One back from that. Right, one more I think. Every circuit should really have LEDs, I think. That's the only way you know anything's ever happening. So this goes the end of that to that 100k there. So the end of that. Come on, get that to there. Okay, so theoretically, that should be in.
You are missing the potentiometer on the right.
Oh yes, I was going to ask you which one would it be? Are they all the same?
So probably, I think they are, but 100k should work.
I've got a 25.
I think it should also say, like in the text, I think I mentioned like which one it is. If you want to check that. Or
Well,
check it.
I've got 3 that are not labelled, so I've got a 10k, a 25k, a 500k, and 3 non-labels, which I assume is the 100. These are.
Yeah. If you look at them from the bottom, they should actually have, yeah, there. If they say B104, then that would be 100k.
I've got an A104.
You can also use that one.
A104.
So the A and the B is like an A potentiometer is always a logarithmic one,
Okay.
and a B potentiometer is always a linear one. And that just relates to, like, as you turn them, like how the resistance increases.
Yes. Okay. Are we going to need to hear anything?
Yeah, so the idea is, like, this is the VCA, right? So the idea is that you feed it a signal, like some oscillation, preferably. And then you take the output from the other socket. And then you should be able, like by turning the potentiometer, to like increase and decrease the volume.
Okay, so for that I'm going to need a couple of things. Luckily I got I've got the original thingy plugged in here. If I can
Nice.
access it. What do I need to do? I need to do something because this is, I can't actually reach it. Go on. So that's there. How can I bring this in without knocking everything over? Oh. Okay, so I need a waveform, you say?
Yes, exactly.
And which is our in?
So I'm pretty sure it's on the left.
Let's turn that down for a minute. Let's see if we've got anything coming through. Not at the moment. I'm just going to bypass it just to make sure we would be getting sound.
Right.
Yeah.
The batteries are plugged in, yeah.
They are, but I've no guarantee that they have much juice going on. But get this here. It's usually my patch sockets that are causing the problem. Let's put this to half.
Yeah, that's a bit annoying. Did you power the op amp?
Well, I mean the power's plugged in.
Oh yeah.
Let me see if there's anything obvious that's missing. So that's going to, and I did get this bit right, didn't I? That's negative going to the top. And that is connected to that, which both gives it the internal. I've got that in over there. That's got 1, 2, 3. That's my 330. It's definitely, I've got a click at that point, which would be an indication that something is functioning. That's plugging into there. That end one is going into pin 1. Yeah. That's 100k going into pin 2. Yeah. That's warm. That's very, very hot.
Oh, the chip is hot?
The chip is hot.
That's a bad sign. You should unplug the batteries.
Okay. Let's run through. Yeah, kind of. Right, come on, let's work this out then. So, let's take this out of here for a moment. In fact, I can take those bits off. So, going across the top, that's my 330. Going in there from the top, 31 to there. That's crossing there to there. That's going down to ground, yes. That's a second going across to pin 2. Number 2, that goes from there to number 3, yeah. And 1 and 2 is done, yeah. 2k comes into that top pin. Goes to the pin outside, yeah. In there I've got that third pin going into there, fourth pin going to positive. I'll come back to the diodes in a moment. This 100 is a 1 and 2. That is that same front end chip. That is a 10k going off at 19. The top, that's going underneath. This one is going to the top, to the one next to it. It's got a jumper there.
Is the jumper like on the middle pin of the chip?
What, this one here?
Yeah, that should be on the middle pin. That in the center.
Yeah, it seems to be.
It is? Okay.
And it's not on that one, which is next to the 100k. That comes back Comes back to there and jumps across. 100k is there, which goes to 3. That one there. It's there, going all the way up to there. That goes up to the top. 100k crossing the bridge over here. That's 5. That's going up to this one, which is going up to there. Yeah, it is. That's 100k. 100k is the same as on the 2k, and that goes up to the 1. Right, I'm just going to pull out these diodes and try those again. So that's that way around. To go to there. Got one next to it which is going the other way around to one after it. Another one which goes from its leg to one away from that one. Another one goes from its leg to next to the 100k. One down here, which is that leg to the leg next to there. And one more which straddles, goes that way around, goes to the 100k. And that one. Well, it seems right. Let's try that again.
So with the batteries, you're sure that you have the positive rail on the top and the negative rail on the bottom?
No, I will check that.
All right.
I think would be good. Let's see if I can do a little bit of a. If I get my meter out just to make sure what we're doing. So. Well, let's just look. We've got, so they're on the batteries, right? I suppose. So if I set this to DC voltage, and put it on that one. So I've got one here. So that gives me 7 volts.
Should be enough.
And that doesn't give me anything, so I'm not actually connected to it anymore, am I? I'm not doing that quite right. So then both negatives on the battery should be ground, yeah?
Yes, but you want to, like the best idea is to start off with, oh, Jesus Christ, this really doesn't work. This is really not working. I think you can hear me now. So basically what you want to start out with is the positive rail and the negative rail. So you want to grab the red wire of one battery, and you want to plug that into your positive rail. So for you,
that should be this inside one here, shouldn't it? Put this here. That should be the positive rail.
Yes, you take the positive. Yes, you plug it into that one because that's your plus. And then you want to take the black cable from a different battery.
Yeah.
Same battery. I'm sorry.
Yeah.
You want to plug that into your ground, basically.
Okay, so the ground is.
Already did. right? That's your
Yeah.
ground. Yes.
Yeah.
Then you want to take the red cable from the other battery
Yeah.
and you want to plug that into your ground.
Oh, that's what I've got backwards. I've got me two black cables tied together. That's what I've done wrong. That's what I've done wrong. Okay.
Right, and then the black one into what's supposed to be ground. Yes.
Yeah. Okay, good. We had something that was wrong. That means it's fixable. If you can identify that something that's a problem, that's always a good thing in my book. Right, let's just go back to my diagram. Okay, I'm worried that'll be loud. I'm just going to turn that down over there. So this fits in here somewhere. Look at that.
It works. Amazing.
No, my breadboard isn't upside down at the start. You have to go back to the start to understand what it is that's different with my breadboard. It's not upside down. It's just that the labeling on my breadboard is different to the labeling that's on the breadboard in the manual. And so that does create confusion. But ultimately what I'd had my black and red backwards. I mean, it's a simple mistake to make. That's all it is. But but there we go. Okay, what are we doing again?
So we made a VCA.
Yeah, we did. Look at that.
Yes. I mean, a year ago, this was like the main objective, right? Now we
Yeah, no, totally.
Yes.
So yeah, and our pot here is changing the level. Very simply.
Exactly. Now you could even like, since you what you have there is a voltage divider. It's a voltage divider, right? So you could also replace that with a socket, and you could feed in like a voltage from your modular, and you could modulate the volume with that. So it's a fully functioning VCA, basically.
Yeah, gotcha. Steve, if we did that, then we would have none of this drama, and we have to have drama, or what's the point? What's the point?
It's the fun in that.
Yeah. So yeah, what's next?
Good question. Yeah, I think the next part is the volume detector. So basically, if you think back to like the thing with the building blocks in the beginning,
yeah.
Basically now we have the volume modulator. And now we want to like know what's the output volume of the signal that's coming out of the thing. And this is an interesting problem to solve, because you can see it there in the manual. You can see like the waveform. So basically what I did is like I just took a snare out of my DAW, and I just like looked at the waveform. I just like redrew it. And this is how that particular snare looked. And the question then is, what we want to answer is like, how loud is the sound? And if I ask the question, like the first response is probably like, well, it depends, right? Because the sound like on the left side is louder than it is on the right, right? You can see that over time, like the volume drops down actually. And so whenever you ask the question, like how loud is the sound, you have to specify like at what moment and for what interval, basically. And so that is kind of like what we have to do with our circuit. Now, at first, like for this first iteration of this little sub-circuit, we're going to take a little shortcut, because this will like become clear in a second. But we can make our lives a lot easier if we say we're going to cut the waveform in half, and we're going to throw away the lower half, and we're just going to look at the top half. Basically, you can see that down there, like in the second diagram. So that's what we're going to do for now. If you scroll further down, this is the part with the time. That kind of illustrate like if we look at a very, very short instance of time, it's very hard to tell like how loud the sound is. So if you scroll further down, You can see here, this is the circuit that we're going to use. This is a circuit that people call a peak detector. And the way it works is very simple. So you can see it's only made up of 3 components. So you have a diode, you have a capacitor, and you have a resistor. And then, the direction is backwards on this. People complained about that. But I put it this way because, like, in the end, in the diagram, it's also pointing right to left because it's coming from the output and going back to the input.
Okay.
You can see that on the right, we apply our oscillation. And then on the left, we get our volume. So it tells us, hey, the volume of this is 5 volts. And the way it works is that, as we probably know, like a diode is like a one-way street for electricity, right?
Yes.
So electricity can only flow in this schematic, like from the right to the left. The other direction is blocked. And so what will happen if we apply a voltage like to the right side is that a current will flow through the diode and into the capacitor and will fill up the capacitor. And that will continue until the capacitor is filled up, like until the capacitor is so full that you can't push more current into it, basically. And at that point, the voltage on the left will be roughly the same as the voltage on the right when the cap is full. And now the kind of magic happens, like if you apply this oscillation, the oscillation will kind of like go up and down in voltage like very rapidly. And every time it goes up in voltage, it will push current into the capacitor. And every time it goes down in voltage, current will drain out through the resistor. So it will come out of the cap and it will go through the resistor into ground. Now what we'll do is we'll choose like a very big resistor so that kind of like draining out process is very slow. And so that means that as long as the waveform is like returning to the same peak in rapid succession, the voltage inside the capacitor will be like roughly the same because there's not enough time for it to like meaningfully drain out. So as long as the oscillation is going to the same peak, the voltage is going to be roughly stable. But as soon as the waveform kind of like dies down, it gets more quiet, and so it goes to like a lower peak, that will kind of open, that will kind of create an opening for the cap to like discharge in a bigger amount. And so then the voltage will kind of slowly drop to that new peak that we have in the waveform. And this way, like if we monitor the output voltage, we can constantly see like how loud on average kind of the waveform is in that moment.
Okay.
Right, and here basically I just explain like this process, so you can scroll down further.
Yeah.
Right, if you go a little bit further down, if you go to the footnote, there is a link in there where it says right here.
Yeah.
If you click that, then we see the simulator. And here on the left, you can see that in action, basically. So what happens there is that we apply a triangle wave to the input. And it's swinging between plus and minus 5 volts. And on the right, you can see that we get a steady 4.4 volts, roughly. And you can see, like, it's a little bit hard to see how the cap gets filled up, but you can see how it's like constantly kind of draining out.
Yes.
But what happens is that it slowly drains out, but like every time the waveform goes into its high phase, it gets topped off again. So it's just like a constant stream of just like filling it up and then slowly draining it. And the issue that we have with this is that, you can see on the left, like the actual volume is, or if you want to call it that, the actual like peak is 5 volts, but the peak that we measure on the right is actually 4.4 volts. So that's less than what we have on the left, right?
Yeah.
And the problem here is the diode. Like diodes have like this pesky characteristic that they have something called a diode drop. And the idea with that is that if you apply, let's say, 5 volts to the input of a diode, you will not get 5 volts on the other end. You will lose a little bit of voltage. Okay. So that's roughly around 600 millivolts. those are just gone. You can think of that just like as if the diode was eating that up. So it's just dissipating, gone. And this is, in our scenario, this is not great because it means that our measurement is not accurate, right? Because we want to read 5 volts, but we read less than that because of the stupid diode. And so we actually have to find a way to kind of like outsmart it, to kind of like make it not drop the voltage. And the way we do this is with an op-amp, actually. You can see that on the right. So I called it here a precision peak detector. And the precision refers to like there's no error in the measurement. You can see that like on the left, again, we have the 5 volts peak. On the right, we actually measure 5 volts, like 5.001, whatever. But yeah, it's like almost perfect. And the way this works is, Robin, you probably recognize the op-amp setup, kind of, because it's almost a buffer. Like if the inverting input, the one with the negative sign, if that was connected straight to the output, it would just be a normal buffer. So it would just be reproducing whatever voltage you apply. But we do this like neat little trick where we actually connect the inverting input to the point after the diode. And what that does is, so in a very simplified way, if you set an op-amp up like this, what it wants to do, if you want to like treat it as a human being, what it wants to do is it wants to make its 2 input voltages equal. So if we imagine we stop time and we say, okay, so we have a straight 5 volts applied to the non-inverting input, to the plus input, then the op-amp will try to make the voltage at the inverting input, so at the minus sign, the same. Now, the thing is, if the op-amp would just be pushing out 5 volts, the stupid diode would again lose, the voltage. It would drop it to 4.4 volts. And that is obviously not equal to 5 volts, right? So the op-amp would be kind of dissatisfied, if you will, because it's pushing out 5 volts, but it's getting 4.4 at the other input. And so what the op-amp does is it basically says, okay, then let me just increase the output voltage until I get 5 volts at the inverting input. And so what it will do, it will push it up so much that what the diode is losing is compensated, basically.
Yeah.
And so then, after that, we have to get 5 volts to get like this equilibrium. And that way, like we just neutralize the voltage drop.
Yeah, gotcha. No, that makes sense.
Nice.
Oh, we have Simon the Magpie in the chat. That's very exciting. We have to take a moment just to bow before the magpie.
Yes.
That's awesome to see you here, Simon. Thanks for popping in.
Yeah, hi, Simon.
So yeah, that's, I understood everything that you said. 'Cause I was imagining myself sitting here doing this by myself, trying to compare these 2 diagrams and just going, I don't really understand why this is different to this one, but we'll just move forward. But from everything that you've said, that whole business with the op-amp trying to equalize itself, I totally get what it's doing. I don't think I've got that before, so that's fantastic.
Nice. Glad to hear.
Yes. So what's next?
Well, the next thing would be that we set this up on the breadboard. And it's actually like a small change, right? Because it's not that many components. And I did something, I don't know if you also complained about this, but some people complained that it was hard for them to follow the breadboard layout because I didn't previously mark like which parts are new. And so what I tried to do here was like to say, okay, so the grayed out things, you've already done those. You don't have to care about those. So only the other ones are the ones you have to add.
Yeah, that's quite brilliant, actually. That is extremely helpful because, I did get lost in that sometimes. And also you weren't sure, had something moved? You wanted, because it did happen sometimes, you did have to compact it a little bit, or when you're replacing part of the circuit with something else, you did have to make a change. So yes, this is very, very useful. So, all right, a bit more fiddly faffling about then. Hang on, let's get to it. I'm going to take that fella out again. I'm just going to disconnect the battery for a minute because that always seems like a good idea. Let's get back our overhead. So we are pulling, oh no, I've taken that out now. We're pulling our pot comes out. Yeah, the pot's no longer there. So that comes out. These bits come out. So that there's bits which are no longer there, yeah?
Oh yeah, true. Like I removed
The pot.
potentiometer, right? The voltage divider.
So I can get rid of those bits. So that stays. That's my the 330 also goes by the looks of things. Yeah.
Oh yeah, yeah. That was also like part of the voltage divider actually.
So that is there to there to there to there, and this comes in on that bit.
You do have a oscilloscope, right, Robin?
I've got the NTS2, which is now the oscilloscope
Oh,
of all modulars.
yeah.
So
How's
yes,
that working?
good actually, because I have a cheap Chinese one that I bought, and that has worked quite well. I've got a lot out of it, although I don't really understand what any of the buttons do, so you're fiddling around trying to make it work. With the NTS2, it's all suddenly much clearer, and you understand what's going on, so it is much easier to use. My largest criticism would be that it just stands out a bit too much. So you put it next to your modular, and all you can see is this bloody thing, whereas you want to be looking at the lovely glowy lights. So it's a little bit. I might have to colour it in black or something, but
Right.
we'll get to that in a minute. So 41 to there. To the outside. Num, num, num. I want a slightly wider one. Come on, quick time, quick time.
You might notice that like the layout here is very odd, and that's actually because I think that was after the VCO video that you did or the live stream. Like there, like you were very upset about the fact that like so much changed between chapters,
Okay.
and so after that, actually, I made it a point to always take the finished thing, like the full layout,
Yeah.
and then just take things away. Just work backwards. And that's actually, it works quite well, but the issue is that you get like these very odd things where all of a sudden, like, the other op amp is on the other end of the breadboard for no
Right.
discernment.
But we're just blindly following at this point. We're not. At least I'm not. I'm not thinking about where things are going particularly. I'm just trying to follow the numbers and put things in the
Right.
right place. So we now
Yes.
need the 72 bloody eyes. Is that a thing? I can't see for looking.
Well, if it's a small chip, then it's the right one.
Yeah, let's call it that. And there's the dot. So the dot's going to go here, right on the end, 55. I'm going to need to give it a squeeze.
That was actually nerve-wracking because like when I set up this final layout, the problem is like this drawing that I've made at some point only goes to line 55. And
Yes.
so this means that like when I do the layouts for the manual, I can only use the space up until that point. And I really wasn't sure that I was going to able to squeeze it in there. And it was like really by a hair that it worked.
It goes there. There's another brown. Crossing the streams at this end. That's there, that fella's there. Oh, I need 100k. So K comes off that leg into that leg. Got a weenie one. It's got to go in there. Goes to line, goes to 50.
Robin, I'm curious, did you like in school, like in physics class, did you ever do any breadboarding?
Not not that I can remember. I did an electronics O level, which was very unusual back then in the 1980s at school. But it was kind of an extension of physics, I suppose. I don't remember breadboarding. In fact, I mean, for some reason, I remember these huge things, the great big copper slabs that you would put between things to make a light bulb work. But I'm sure it was more complicated than that. But what I do remember from it, as much as anything, is NAND gates. And you know, making every gate out of NAND gates. That's the one thing that seems to have come back because we use logic in modular.
Yeah.
You know, and that's come up in computing and all sorts of things ever since. So that's been the one thing that seemed to be useful, was being familiar with the concepts. I couldn't tell you how that works all the time, but I at least understood the idea. That was the. I don't think I did. I mean, but having said that, I knew what it was, and so I must have come into contact with it at some point.
Right.
But at university, I did my degree was musical instrument technology. So I did electronics in there along with woodworking and flute making and things like that. So I had to do a strange mix because we were dealing with acoustic instruments. Like I built an African xylophone as one of our projects, as well as building a recorder and a flute. But I also did electronics alongside that, and we studied sound tools, you know, pre-Pro Tools, and we had a Fairlight and other bits and pieces that we got to use. So I do have electronics in that, and I did print my own PCB to do a sound to MIDI converter, which was my final project. I got to play the examiners my flute that I'd made with my MIDI to sound, my sound to MIDI converter, playing through a Korg M1. So that was quite exciting.
And when you say you printed the PCB, like do you mean like you etched it?
I definitely used a piece of software, but it was then printed onto acetate, and then the technician did something with the acetate to produce the PCB at the end. I can't remember what that was.
Right.
That process. It was a chemical process anyway, something to do with the acetate was mounted on something and it was bathed in something.
Yes.
I don't know, technical terms.
But you didn't have to deal with any chemicals.
No, I didn't have to do that bit. I just produced the print.
All right.
But you know, computers are funny in those days. I mean, the internet came into being while I was at university, so we had text-based email in my first year. By the second year, the web had been invented. You know, just like very, very strange times. And then by the third year, we were playing Doom over the network in the library. So you know, it's amazing how fast things come.
Yeah.
So that to there, that to there, that to there, that to there, that to there. That's going to there. That's across. That's to that line. That's to there. I've got this 1 in 5. No, that must be one. No, I don't know what that is. That must be a capacitor, because we need a capacitor, don't we?
Yeah, we do. So Alex asked, if we were to put an oscilloscope before the diode but after the op-amp, we see a voltage higher than 5 volts to compensate for the diode voltage drop. Yeah, that's actually exactly what you would be seeing. And you know, the cool thing about it is every diode will have a different amount of voltage drop. You know, they're not the same. So there's like slight variations in there. And the cool thing about this feedback trick with the op-amp is that the op-amp will find the exact voltage it has to push out to get 5 volts on the other end.
Is this a fellow that we need?
Which one?
That's
a 1 microfarad capacitor.
Yes.
So if that's in the schematic, then yep. Oh, it might be 1.5 that we need. I think this might actually be the 1.5 one.
I think it is.
Yeah.
Yeah, J63, 1 something 5 it says. So that goes from there to there. So in my little circuit here, so this is my op-amp. That's my diode that's coming through. So that's being, the output of that's been fed back into that pin there. And the circuit's continuing through the capacitor and the resistor, which is then popping over there to ground. Look at that! I know what that's doing that thing and that's doing that. Yeah, that's exactly how that should be doing it. That's going to there, that's going to there. Yes! I need to put this socket back in, which is there. That end goes in there.
Right, so in this scenario, it's actually not so much about hearing the output.
Okay.
But what we want to do is actually we want to take an oscilloscope and we want to look at the output of the peak detector.
Okay. So where are we measuring?
Well, I mean, ideally, if you do have 2 probes, it would be great if we could, for one, measure the output of the VCA, so what we're feeding into the peak detector. And then on the other end, we want to measure the output of the peak detector.
Doopy doopy doo, doopy doo. I'll need something like that. Let me think about this a second. Well, I mean, where am I trying to get to?
So first tell me, like, what kind of probes do you have, like, on the oscilloscope?
Well, at the moment I've just got a patch cable, but I can touch it on the end of something else, which is plugged into something else.
Okay, that's actually not bad. So basically, you can just like plug that into the output of the VCA. So what right now you're feeding into your speaker or mixer, just feed that into the oscilloscope.
Yeah, I've got that. That's what we're seeing. So that's coming from this purple bit.
All right, great. And then what you could do is like you could take another one of these jack sockets from the kit.
Oh right, yeah, that's a good idea. Look at that, that's a good idea. Yeah.
And put that into your breadboard. And then I'm guessing you will have to, maybe put it down there, like near the 1.5 capacitor, like maybe on the left side of it.
Yeah.
Right. And then we want to, I guess, first up, like connect the outside wiry one to ground.
Yeah. Yes.
Is that, I think you're like one off from where it's plugged in, right?
No, yeah, and I'm going, yeah, no, that's right.
Are you sure?
I
Also,
think so. I mean, it's a slightly overlong cable. I can use something which is a bit more appropriate, size appropriate. Hang on.
right.
What was that? Let me get an orange. So, oh, let me think. Yeah, because I was going horizontally. I need to be going downwards, don't I? That's what I was doing wrong. So I need to be going here.
Yes, exactly.
And then that needs to be going up one into there. Oh, see, get the appropriate thing. Get the appropriate thing, and then it's going to work all right. It's evidently getting late. That's the thing. All right, try that. See if that works.
Perfect. Oh, but I think you've plugged it into the positive rail now, no? Or is it the red one or the blue one?
It's the crying out loud. Come on, we can do this. This is modding on the go. It's the inside lane, yeah.
Wait 1 second. So
yeah.
Let's check with the rest of the circuit, right? So we can see that you connected the cap also to the red rail, right? So that would indicate to me that maybe for you the red rail is actually ground here.
Here, yes, the red rail, the inside is ground on this bottom one.
Yeah,
inside is ground.
Then we want to connect to that. Yeah, you were right. Sorry.
Okay.
Very nice.
And then we need to go to get a signal.
Right, we want to connect that to the other side of the cap, like not the side that's connected to ground, but the other side of the cap, basically.
Okay. Let's try to adjust this so you can see, because this is very annoying. This cable is going over everything. Okay, so this should give us a second output, which it does. Now, see, the question is, you're gonna ask me what it is that any of this is actually saying, and I'm not 100% sure. I've lost that. There it is. So yes. I've got the blue trace is the signal coming in, and so I must be controlling the blue one at the moment. So that's set to 2 volts, and the other one's set to 5 volts. So let me see if I can work out how to go to the next input, horizontal, vertical. There we go. No,
yeah, I think
that's not it.
I think the scaling is off, right? Because your oscillation you're looking at. No. Yeah.
So now we've got, because it's input 1 and input 3 ultimately, or 1 left and 2 left. So they're both now set to 2 volts, and we can see that our sawtooth is doing the thing.
Right. Can you reduce the scale? Yes, perfect. Right. You can see that. Did you reduce the scale on both channels?
It's just a flat line, isn't it? So would it make any difference? Yeah, it is on both. It's not defined on the horizontal axis.
All right, but we can see basically what we're expecting to see. You can see that the green line. Oh my God. This is really.
Yeah, I'm sorry. Yeah.
It's fine. So we can see that the green line now shows us, like, it tells us how loud the signal is, right? Because the sawtooth wave, the peaks, actually match up with the green line. So that means that we actually have like a solid volume reading that tells us what reality is, basically.
Yes.
Yes.
Good. That's very effective.
It is.
Right. Nice. I mean, I don't know about you, but we should we should probably, is there a point that we could come to where we can, where would be best to go to from here? Because we don't want to keep going on all night. We've done a couple of hours, which is great, but
Yes.
we should probably try to find a way to, I don't know, what else could we show within, say, the next 20 minutes, half an hour?
That's a good question. Maybe can you scroll down in the manual
Yeah, one sec.
just to check what the next chapter is actually? Okay, so we get the subtractor. Can you scroll down further? And a little bit further. Right, and here we would actually see the effect. So if you scroll down further, that's a bit annoying. Like if you go back up again. So actually what we're adding is not a lot. If you go one chapter up. Right, so here, like that's the meat of what you have to add. And then the next section is just one jumper, just like tying this section to the first section. So if you feel comfortable with setting this up real quick,
Yeah,
then we would get the compression action. Like we would get like a limiter basically.
let's do that. Let's do that.
Very nice. While you do that, I can just quickly explain like what we're doing. So
go for it.
if you think back to the functional blocks that we had in the beginning, we now, on the breadboard, we have two of them set up. So we have the, what I call there, the volume modulator, and we have the volume detector. That's the peak detector. And so all that we need to do now is like we need to take the volume that we measure, we need to compare that to a threshold, and then we need to take the result of that and use that to control the VCA, right? Because the first block that we set up is already VCA, so it already reacts to control voltage. And so the way that we do this is with something called the voltage subtractor. And that we can make out of an op-amp and just a couple resistors, and that's what Robin is going to set up now. And the basic idea there is just that it's a little circuit that you feed two voltages, and then it really just does what the name implies, so it just subtracts them. So in our case, imagine that we have the sawtooth wave that we just fed into the VCA that peaks at 5 volts. Then our volume reading would be 5 volts. And then on the other side, we'll take a threshold voltage. So let's say we take 3 volts. And we take both of those and we feed those into our voltage subtractor. Then the subtractor would say, okay, let me take 5 volts. Let me subtract 3 from that. And the result would be 2 volts. And then if we take those 2 volts and we feed them back into the VCA is actually set up to reduce the volume as the the control voltage increases. So if we give it a positive control voltage, 2 volts in our scenario, that would mean that would really violently reduce the gain of the VCA. And that way, like in a very like rough way, we already have what we're after. So we reduce the output volume if it goes above a certain threshold. But yeah, I must say I'm pretty happy that your op-amp chip didn't die. Because usually when they get hot, like that's a good indication that they might have.
Yeah, I get away with stuff.
I noticed.
This one, past leg. 1 past. That goes over. A couple of things over here, and I've got to find a 470.
All right, because all the other ones were just 100Ks, right?
Yeah. Not convinced that's going in. Let's find another one. That's what I want.
Okay, so Alex asks in the chat, is the peak detector optimized for a certain frequency or frequency range? So not really for a frequency range, like
Right, that goes, that's a single, that goes to there, that's the 100, I need a 470. That's my 10Ks. Where's my 100K? That's my 10Ks, that's my 100Ks. Out of the way.
Sorry, I disappeared again for a second. So, Alex, I was just addressing Alex's question. Alex asks if the peak detector is optimized for a certain frequency range. And it's not really. So the values that we've chosen here, they are basically just setting a release time, if you will. So by choosing like a certain size of capacitor and resistor, it takes a certain time to like drain the capacitor, so to make kind of the detected voltage drop. And the slower that drops, like the longer the release time is. If it drops super quickly, you have like a super fast release. If it takes a while, it's a very long release. And here, just for this setup in particular, where like that's not changeable, so right here it's fixed the time. I just kind of made do with like the components that we have at this point to have something that has like a not a pleasant sound, but you know, just something that you can just see how it works. That's all I went for there.
Okay, that's not right. That needs to go. That needs to go across one. Okay, nearly there. That's a 470, that's a 470. I've got to get a pot in there again. Where's my pot? Which one did I use? This one.
I think this should be a 10K, if I remember correctly.
Okay. I think that should be in.
Yeah, now there's one more thing that you need to do, which is if you scroll down in the manual to the next breadboard layout. This is a very odd chapter because all you do is like you just add two jumpers, I think. So you still have to do that. And what we do there is like we just connect this voltage subtractor that we just set up to the CV input of the VCA.
Okay.
All right, now the thing is that for the input signal, it would be best if we had something like a drum machine, like a kick drum, snare drum, anything like that. Do you have that?
Dumpy dumpy dum. Hmm. Let me just think. So where's that coming from? That's coming from there. I need that to be the output of the VCA. That. Do we need to be looking at the scope or hearing it?
Well, both could be interesting, I guess.
Both. Okay. This has a through, actually. That's the other really good thing about it.
Nice.
So I can put that in there. Oh, I've just turned it off. Great, brilliant. The chances of this actually doing what I think it might seems a little bit. So that's going into there. That's doing that. That's doing that. That should give me something, but it bloody isn't. So I'll go into there. That's enough set. That's going. Alright, let me just see if I'm getting. Leave that plugged in. That's coming out of there. Let's use that. Is that of any use?
Well, we can try it.
So that's going in to here. Oh, I haven't powered this yet. That will be part of the problem. Okay. And I need the through now going back to that, which is here.
Right, and now if you play with the potentiometer that you just plugged in, should have an effect. Right, so the issue right now is that the sound doesn't really have like a decaying voltage, decaying volume really, right? It's more just like a burst and then it just stops. And so...
Okay, hang on, I can do better.
That's good. Can you, like on the oscilloscope, can you reduce or can you like make the time frame wider that we're looking at?
Yeah.
I think you made it narrower. Yeah. You zoom out even more. And even more. Righty. That's good. And now, if you play with the potentiometer again, right, you see that? So the front part gets squashed, but the back part actually stays the same volume.
Yeah, totally seeing that.
And you can also hear it, like it's much less like aggressive and it sounds much more uniform, I guess. Nice. I'd like to point out to those people at home that I did just create a percussive sound, you know, on the fly from the Erica Synths EDU DIY synth, which is just sitting there. Oh, nice.
Look at that. I've made a drum noise on demand. That's just extraordinary.
What did you use?
Well, I've got the sample and hold noise generator, so the white noise going through the filter. Then I'm using the sequencer to gate the envelope into the VCA. So it's just a little percussive synth voice.
Nice.
And then using the filter, I can go from... Oh, I've pulled it out. There we go. From snare down to kick. Look at that. I'm designing electronic circuits. Yeah, so that's really good. So we are,
Right.
yeah, we're definitely seeing that. Nice. Don't blow stuff up.
And that's actually like, this is actually just how the thing works. So everything that would come after this is just like adding bells and whistles. You know, like making the attack controllable, making the release controllable, kind of tidying up the sounds a little bit, adding LEDs, whatever. But it's like, this is it. Like this is the thing. That's all.
Nice. And what you end up with a bit of luck, is this fella here. Actually, see, I could have done that under the camera had I thought about it a little bit more. But no, hey, there we go. So that, and all the stuff on the back, is what we've done. I mean, that's the magic of what this series has been about. Really, is that you've got to take this stuff that you put together like painting by numbers, like following an Airfix kit or a Lego instruction manual. You take that idea and then you build it out to the point where you actually can start to grasp how these things work together. It's been extraordinary. I mean, I spoke to Gertz about this a couple of years ago. During the pandemic, I had him on, and he was talking about this idea for new DIY stuff. And part of that was him saying to me that he doesn't believe I know anything about it. I haven't learned a thing about electronics, even though I've built all these modules. And he's absolutely right. And it wasn't until he got together with Moritz and started producing these that I've actually started understanding more. I'm still not there, but I understand far more now about circuit design and how these things work, and that never would have happened, I don't think, just by building kits. You don't really get that sense at all. You can be completely oblivious to how things are working. You're just building the stuff, soldering stuff together, which is nice in of itself. But this has been an extraordinary series, and I'm so pleased that there's some more. It's been great. So, I mean, I think, where am I? I think that's, no, that's not what I want. Hang on a second. You're way over here. We don't bump. Is it that one? There we go. So yes, I think that's probably a good place to finish. Don't you think? Have I lost you again? Oh, see, that's a shame.
Sorry.
Oh, he's back. That's
Yes.
all right. So yeah, that's a great place to finish it. That's been extraordinarily useful, Moritz. It's been really interesting having you on. I wasn't quite sure how it was going to work because I just bumble on and bumble through these sorts of things. But it's been really, really valuable having you on here. So thanks ever so much for spending your time with us this evening.
Yeah, sure. It was super fun. Like, I really enjoy actually getting like the feedback from you also in the previous videos to like just kind of see how someone who's new, who hasn't thought about the manual before, like interprets the stuff and the challenges that you face and everything. So it was really helpful in like coming up with better ways of writing the manuals actually. So yeah, thank you for that.
Oh no, you're welcome. I mean, that's funnily enough, that's something that happens a lot. See, that's not me, is it? That's me. With other things that I do, working through kits for people and other bits and pieces, because I don't have a lot of pride or ego when it comes to this. I'm not trying to make myself look good. I'm just really much more interested in the process, and so I don't mind hitting problems and showing them because I'm not trying to cover anything up. I'm not trying to market something. I just find it really interesting, and if my blundering through something is helpful ultimately, then that's brilliant. And also the people in the chat as well have always been enormously helpful. They're such a supportive bunch, and they sit there, they go mad pointing something out that I've done wrong as I'm obliviously trying to plug all these things together. And they're superb at that. They're a great little support group for these meanderings, I would say. So yeah, is that good for you?
That's great for me.
Great. Lovely stuff. Well, do get in touch if there's another one, if you want to do this again, because I'll definitely be up for that down the line. Kick drums and stuff would be very interesting. So yeah, give us another shout if you want to do this again. That'd be great, and I'm sure we could do something just as fascinating.
Yeah.
Great. Right.
Yeah.
Well, in that case, mate, I will let you go. Thanks ever so much for that. And yeah, we'll talk soon. Are you at Super Booth?
Yeah, actually, I'm doing a workshop there.
Ah, nice. I'm just there on the Saturday. I don't know how. I don't have any plan. I'm just wandering about and poking around. So I may see you there. We'll see how that goes.
Yeah, I will probably be hanging around the Erica booth.
Ah, yes. Me too at some point. Well, it depends. If he's got that horrible stuff, that lovely liqueur that I might stay clear. I don't know. That was an odd start to my day. That was, I can tell you. Super. All right. Like I say, I will let you go. Thanks ever so much. And I will be in touch, and I'll just finish off this stream by, I don't know, talking nonsense like I usually do for a moment. So thanks everyone for coming into to the chat and joining us this evening. That's been modular DIY, building a bit of a compressor out on a breadboard. That is very exciting. I thoroughly enjoyed it. I think 2.5 hours. That's not too bad for us, I don't think. So great. This is available on the Erica Synths website. The compressor, and the manual is there if you want to go through it yourself and just check it out anyway. And you can build the kit directly into the module, or you can build it out on a breadboard as I have here, using exactly the same components. All of these components come from that kit. That's the whole point of it. So that'll do us, I think. Where are we now? Nothing else happening. Super Booth is upon us shortly. I do have something coming out this week, which is exciting. So I've got something hopefully on Thursday with a bit of luck to show you. So I'm beavering away at that tomorrow to try to get that finished. It's not a big new thing. It's a small, you know, it's just a small new thing. But so that'll be later in this week. Otherwise, I'll try to squeeze. I've got a couple of builds I'd like to do before Super Booth, and maybe another review. I'll see what I can squeeze out, but I think we might be overwhelmed with news, which is probably what's going to happen next. So we'll see how we go. If not, I'll probably be telling you all about my Super Booth experience, which will be exciting in a couple of weeks. So great, thanks. I'll stop rattling on, let you go. Have a good weekend. Hip hip the king and all that. I don't know what's going on with that. And I'll see you soon. So yeah, go and make some tunes. Let me find my outro, and I'll let that go. Which one is that? Is it that one? Which one? Which number? Number 7. Number 7 coming to you shortly.